Record. Yeah, okay. So we're going to begin our discussion, continuing our previous discussion. Now we arrive at the section 2.4. We will discuss about the nonlinear optics, which will be presented by me. Okay, so for the introduction part, I would like to recall some concept that we have previously discussed about the nonlinear susceptibility. The first one, when we talk about the nonlinear linear media, we only talk about the linear susceptibility. And we have defined this relation of the polarization factor to the electric field factor. And it has some kind of linear relation like this. And this linear, in this linear relation, we have the chi here, the term chi. This is the linear susceptibility of the material, and sometimes it describes the refractive index of the material itself. However, this equation number one here, is only valid if the amplitudes of the electric field or the intensity of the light is small. In some nanostructure, nanomedia, nanoscale waveguide, or fiber optics, the intensity is quite large. And it can trigger what we call the nonlinear interaction between them. And the equation 2 here is the relation which is much more general than the equation 1. In the equation 2, we have the relation between the polarization factor to the electric field, but not only the first order term here, but also the second order term and the higher order term, which is the third order, and so on. And we may as well see here, the more increasing the term of the what the order of the electric field, there are new term appears, which is the chi2 and chi3. Chi1 is the linear susceptibility, which I mentioned before, while chi2 and chi3 here respectively are the second order and the third order nonlinear susceptibility. And this is a tensor as well. The first order susceptibility or the linear susceptibility is a tensor which have a dimension of uh, 3/3. So it's a two-dimensional matrix. While the second order and the third order nonlinear susceptibility increasing in the dimension of the tensor or the rank of the tensor. The second order susceptibility is the third rank tensor, and the fourth order susceptibility is the fourth rank tensor. So the more increasing the electric field amplitude relation to the polarization, the tensor which related the nonlinear interaction also increasing in order. Okay, so this is about the introduction about the nonlinear susceptibility. So we can also rewrite the equation number 2 in terms of the nonlinear polarization like this. So we can express them as the equation 3 to 6. And the equation number 6 is the nth order of the nonlinear polarization. Well, basically this is just a power series expansion, but we usually when we talk about the nonlinear optics, and especially in the guided media such as waveguide, we only talk about up to the third order nonlinear susceptibility or third order nonlinear events. The higher order require a much more larger power of light or much more larger intensity. And the higher the order, the less likely it will happen. So the possibility of this process to trigger is relatively small. So we only talk up to the third order interaction. Okay, so for the n larger than 2, we can call the Pm is the nth order of the nonlinear polarization and the Km as the nth order nonlinear susceptibility. Okay. In case of our daily life, when we use some material such as silicon to guide the light or made some glass using the silica, which is the silicon dioxide, we usually only care about the linear effect because when we direct the light into the some kind of media such as glass like that, the intensity that arrive at the media is very small usually. So we only see that the linear effect is much more dominant compared to the nonlinear effect. So Yeah, that's why in our daily life we rarely see the nonlinear effects in such a media. Although some materials such as silicon and silica is in fact a nonlinear materials, but this effect of the nonlinear interaction can only be triggered when the intensity of the light is very high, and usually it happens when we deal with the nanoscale waveguide system. Okay, is there any questions so far up to this point?
Sorry, a question.
Huh? No question.
Yes. Can you hear me?
Yeah.
Okay, so does this susceptibility part, the chi,
Yeah.
depend on some kind of variable? Like, I don't know, perhaps what are the variables that
Oh, okay.
affect this susceptibility?
So the susceptibility tensor may differs from material to material. It is in fact depends on the frequency of the light. Okay, it depends on the frequency of the light. That's why when we talk about the first order susceptibility, the linear effect, we can see the dispersion. The dispersion is the changing of the refractive index, which depends on the light frequencies. So when the light frequency changes, the refractive index will also changes. And that change of the refractive index dependency to the frequencies can happen because the susceptibility itself, which relates to the refractive index, is also frequency dependent. Okay, so it may change depending on the frequency of the light. And also because this is the material properties, be it the linear susceptibility, second order, or the third order susceptibility, it depends on the material geometry. So it depends on the crystal structure of that. Uh, uh, I may give some information about the second order and the third order susceptibility. For the third order susceptibility or the third order nonlinearity, it usually only exists when the material has some kind of inversion symmetry, so point symmetry, right? But in the second order nonlinearities, it happens when the material doesn't have that kind of point symmetry or inversion symmetry. So the symmetry of the material also play into roles to the dependency to the susceptibility. Is that answer your question?
Yeah,
Yes.
for now.
Okay.
Sorry.
Farhan,
Okay.
do you have any other question?
Can you move to the previous slide?
This one?
Yeah.
Yeah.
As we can see in the equation two, the electric polarization vector depends on E squared and E cubed. What is the meaning of E squared and E cubed? Is it like dot product? For example, E squared, does it mean that it is a dot product between the electric field, or is it like what kind of product? Because it will be multiplied by a tensor, right? And the what I want to see is that the overall product of the second and third nonlinear term is going to be a factor, right? Yeah.
So actually, it's hard to see it using this equation number two, but when we use the some kind of tensorial notation, like the chi2 will have some kind of ijk index, and the e will have some kind of I and j index, and then we do the summation so that it's not only dot product, but some kind of interchanging between the terms. I don't know how to say it, but when we express it using the tensorial terms, it will be much more easier to see it that way. So, like for example, the chi1. The chi1 is the two-dimensional matrix, right? So it has only two index, I and j, and then the e itself is a vector, so it has one index only. Let's say I, and then we do the factorial summation, and then the p polarization vector will only have some kind of vector dimension, so it has only one index. Let's say j. So it's much more easier to see it. It's not only a dot product and not only some kind of multiplication of numbers, but it has some kind of dot product multiplied again by a vector and something like that. So it will interchange with this. So it will be much more easier when we talk about it using the tensorial notation. So for the chi2, it has a three-dimensional matrix. So we can write it as x chi, and the index will be I, j, and k. And then for the second order e, it will be we will have two terms of e. The first one is e I, and the second one is e with the index j. So we have two terms of e like that. And for the third order, the chi will have
I
some
see.
kind of four index, and we have three terms of e, ei, ej, and ek like that. And we do the tensorial summation. Now, can you imagine what I am talking about?
Yeah, understand.
Oh, okay.
The problem is that this equation isn't written using tensorial notation. So like usually people write e squared as dot product between two vectors, right?
Yeah.
So
yeah.
that's where my confusion came from. Now I
Yeah.
think I already understand.
Yeah.
Yeah.
So the equation two, I write it this way so that I just want to show that the polarization not only depend on the first order of the electric field, but also higher orders like that. So it's power series expansion. But it is much more formal to do it in tensorial notation. Okay.
Okay.
If there's no question, then I will continue again.
Sorry.
Oh yeah.
One more question. I think I kind of missed it. I don't know if you already explained it or not, but I'll ask anyway.
Okay.
So in the previous slide, you mentioned that this equation applies for a small amplitude of magnetic electric field, right?
This one.
Yeah.
Yeah. And what's your question?
Why does the electric field have to be necessarily small here?
Not really that small. I mean, like, I would like to talk about the not only the electric field amplitude, but the intensity. As we know in the previous discussion, that the electric field amplitude is related to the intensity. Right? Like when we get the high amplitude, then
Right,
we
right.
get the high intensity. So I will talk about it in term of intensity. So this effect of nonlinear interaction will be triggered when we have the high intensity. So let's say that we have 1 hour light bulb, light bulb with the power of 1 watt light bulb compared to the laser with only diameter, the beam is 1 millimeters like that, but it also have the 1 watt power. Which one has the highest strength? Has the higher strength? 1 watt light bulb or 1 watt laser with with 1 millimeter diameter of a beam? Which one do you think?
Okay.
Both have 1 watt power, right? But the laser have higher strength. It can destroy a material because intensity defined as the power divided over area of the beam.
Area squared.
Yeah. So
right.
when we have 1 watt light bulb, the power will be 1 watt, but the intensity will be spread out everywhere in the room. So the intensity is very small. Compared when we have 1 watt laser, and that high intensity will trigger this effect of the nonlinear interaction. To give you a better picture about this, the second order nonlinear interaction usually trigger when we use the laser with the power of in the order of microwatts. But the third order nonlinear interaction usually triggered when you use the laser with power of about microwatts. No, not microwatts, milliwatts power. Like that. So 1 milliwatts power is very small when we use a light bulb, but when we use a 1 millimeter diameter light beam of laser, it is still very hot. So I would like to talk about the equation number one is using the intensity terms because it's just much more pictureable. But as the intensity relates to the electric field amplitude, that's why I write it here using electric fields amplitude. Okay, is that answer your question?
Yes, thank you.
Okay. Okay, so let's continue again to the third slide. Okay, so we have talked about the nonlinear phenomenon, and the nonlinear phenomena is directly related to the nonlinear polarization. The first order polarization is just the linear phenomena. The second order is the second linear phenomena, and the third order is the third nonlinear phenomenon. Now, I will talk about the second order nonlinear phenomena. Let's say, in this case, one, I have a light beam, which consists of two frequencies, two monochromatic plane waves, but they are propagating simultaneously in one light beam. If I have two monochromatic plane waves, then I can write the electric field term as the summation of them, right? The first term, the E1 with the E to the power of minus I omega 1 t is the electric field amplitude of the first monochromatic waves with the at the frequency of omega 1. And this is the second term here is the amplitude of the second light with the frequency of omega t. And the CC here represent the complex conjugates of this term. Okay, so I write the electric field wave function as a complex function in the equations. So the second order nonlinearity happens when I have the electric field amplitude is with to the power of two. So I can see what kind of interaction happens between them. This is a roughly description of them. Is just by taking only this electric field, total electric field, just taking the square of them like this. Okay, so I take the square of the total electric field, and then when I do the square, yeah, I can get this long term. There is very much of combination of term between them because I have some like four of them, right? E1, E2, and the complex conjugate of them. So now after I do the square to this electric field, I get some like 1, 2, 3, 4, 5, 6, 7, 8, 9, about 9 terms. And from these 9 terms, I can distinguish what kind of nonlinear phenomena that happen inside this material based on the combination of omega in the complex phase here. Let's see. The first one is the sum frequency generation. Sum frequency generation is one of the nonlinear phenomena. When I have two light beams with omega 1 and omega 2, they propagate into a material and then they destroy each other from this energy level diagram. They combine and they destroy each other, and then they generate new light beams, omega 3. And this omega 3, however, satisfy the relation that it has the value related to the summation between omega 1 and omega 2. This is what we call the sum frequency generation, so that we generate a new lights with higher frequency, but the frequency is the summation between the first fundamental lights in the equation 10. And the sum frequency generation can be seen in this long term by these two terms. So I have the E1, E2 with the phase related to the combination of the omega 1 and omega 2. And this one also, the conjugate, the complex conjugate of them. This will be the real part, not the conjugate. I miswrite it. So that's the sum frequency generation. We generate new light, a higher frequency using two different frequency of light. This is one of the second order nonlinear phenomena. Another second order nonlinear phenomena, which is interesting, is the difference frequency generation. So this frequency generation is slightly, what I can say, slightly similar to the sum frequency generation. So that shot or what we call, we use two different fundamental lights with omega 1 and omega 2 frequencies, and then we shot it into the materials, and the materials generates what we call the omega 3. But instead of the summation between omega 1 and omega 2, the frequency of the omega 3 relates to the difference between the omega 1 minus omega 2. And This process of the difference frequency generation, sometimes called parametric amplification. Why is it called parametric amplification? Because when we shot the light with omega 1 and omega 2, sometimes the omega 2 here become amplified from the field itself. So instead of it just generate a new light with the frequency of omega 3, it will also generate the omega 2, but increasing its energy like that. So yeah, the power will be increased of the omega 2. Yeah, the process is kind of hard to imagine, but yeah, this is what we call the parametric amplification. Up to this point, is there any question so far? Oh yeah, and one more, one more thing. About this energy level diagram, I did not take it from the Mark Fox book, but from the R.W. Boyd books, Robert Boyd, the nonlinear optics book. So because it is much more imaginable to me to use the energy level diagram so that I can know what kind of the process that happened here. Okay, any question? No question? Handoko, Farhan? Am I still connected? Please answer me.
Yeah, you're still connected.
Okay, so no question. You good?
I think so, but
Okay. What about Handoko?
Continue first lah.
Okay. So yeah, maybe I will just continue again. If there is no question yet. So another term with another phenomena that can happen in the nonlinear order is the second harmonic generation. This is similar process to the sum frequency generation, but instead of summation of omega 1 and omega 2, it is the summation of omega 1 to itself. So in some reference, it may well known as the frequency doubling phenomenon. So we have one beams with the frequency of omega 1, and then when the second harmonic generation happens, the output beam will have the frequency exactly the twice as the frequency of the initial beams. And this process can happen using one single input beams, or we input two beams with both of the laser at the same frequencies. This is this is the second harmonic generation. And the second harmonic generation can be seen when we have the field amplitude is squared, so that we have the E1 square and also the conjugate square, the E2 square and the conjugate of the E2 square. As we can see here, the phase term, every phase term has the twice as much as the initial omega. This is omega 2, twice omega 1, this is twice omega 1, this is twice omega 2, and this is twice omega 2. All of these terms relates to the second harmonic generation. So this is the second harmonic generation, which doubled the frequency of omega 1. And this is the second harmonic generation, which double the frequencies of omega 2. Okay, so yeah, it will generate a new lights with higher frequencies of or higher energy. And the second harmonic generation is a very useful process because instead of generating light with higher frequency, let's say using laser with higher frequencies or higher power, we can use the low power laser, low frequency laser such as infrareds, and then convert it into the visible light spectrum. It is much more easier process than just generating visible power, a visible light spectrum is will have a very high power. Okay, and the last term here is what we call the optical rectification. So the optical rectification, instead of the omega 1 and omega 2 combine each other or difference each other, they destroy each other. and then we can see here that there are no new lights that are being generated in the optical rectification because all of the light destroy each other and then no new generated lights. So where the light goes as the static electric field that is being generated inside the nonlinear crystal. So that initially the nonlinear crystal is neutral and doesn't have the static electric field. But when optical rectification happens, the nonlinear crystal can be can possess an electric field. So it may as well shock us when we touch the crystals if the optical rectification happens. Okay, up to this point, is there any question?
Yeah.
Yeah.
Is there any application to the optical rectification process? Because it only generates static electric field. Like, what is the difference between electric field generated by optical rectification versus the static field that is not generated by optical rectification?
Well, I don't know for sure, to be honest, but if I try to combine what I learned about the stimulated Brewang scattering, the stimulated Brewang scattering happens because there are some kind of what we call the electrorestriction event. So electrorestriction event is that the material will stretch or maybe compress, so or experience some kind of mechanical deformation, not mechanical. So it will deform the material due to the existence of the electric field. So that instead of we deform the material using force, like the mechanical deformation, we deform the material using the what we call the electric field. So maybe the optical rectification, which also generate the static electric field inside the material, will also kind of affect that process of electrorestriction, and therefore it will also affect the stimulated Brewang scattering event. And that's just what I thought. But to be perfectly honest, I have no experience in doing optical rectification. And yeah, I rarely read about it. So that's what I can give you for now.
I see. Thanks.
Handoko, any question?
Yes.
Yeah.
So in the second harmonic generation, you basically combines two lasers of same frequency, right? To
Yeah.
produce something which has the double frequency of the initial laser.
Yeah.
Is that right? Yeah.
Yeah.
I would like to ask you in the actual experiment, how hard is this to be achieved, right? Like, will it definitely generate the, when you combine two lights of the same frequency, will it be 100% create, the laser with two times the initial frequency, or will there, is there any inaccuracy, or yeah, perhaps it won't be 100% doubled or something. Yeah.
Oh, okay. Yeah, I got your question. Actually, I have no experience in doing the second harmonic generation also, and I haven't read any papers about that. But in my experience in doing the forward mixing process, and maybe Farhan also have the experience of the spontaneous parametric down conversion process, the nonlinear process cannot happen with 100% accuracy. Will be some kind of error, like the generated photons will have lower power compared to the initial photon. Although it has a what we call the higher energy, higher power, not the power. The generated photon will have the lower intensity compared to the initial laser that we use. Although it will have a higher frequency. You know, the intensity of the photon itself relates to the how much photon that we have, right? The numbers of the photons.
Mm.
So let's say that we use the intensity of the photons with the intensity of the light with 100 watt per meter square, like that. And then the generated light will only has about 30 watt per meter square intensity. But if the second harmonic generation is happen, the generated photon, although it has a lower intensity, it will also have a higher frequencies. So let's say that we input the infrared and then the generated light will be the visible light spectrum, but it has the slightly lower intensity. Like so, when we talk about the nonlinear material, we also talk about the conversion efficiency. The conversion efficiency describe what we call how much intensity of the laser power that we use that are converted to the uh, generated light. So the process might happens, but the question is how much light are being lost in the process? Like that. Is it an answer question?
Well, I get your idea, but yeah, I was just wondering if, if we were to combine two lights of the same frequency, theoretically it should produce this a new light.
Hmm.
Yeah, perhaps with lower intensity, but the frequency will be doubled, right?
Yeah.
But yeah, in the actual experiment, will it be 100% doubled? And yeah, if not, perhaps what are the factors that might affect this? You know,
Okay.
yeah.
It will not. It will not 100% double. Like I have 100 gigahertz initial input likes, and then the output like will not be 200 gigahertz. Exactly. This process, this effect, we know this effect as the frequency detuning. Frequency detuning happen because of the many kind of factor. One of them is the material dispersion. So instead of the generated light has the 200 frequencies, 200 gigahertz frequency, the frequency will be shifted. Either it will be shifted to the lower frequencies like 190 or to higher frequency like 210. So it will not exactly twice as the initial pump photons due to the dispersion. And of course, there are some other factors which can cause the frequency detuning, not only dispersion. Dispersion is just one of them. Okay, does that answer your question?
Okay. Yes, one more question maybe.
Okay.
The last one.
Yeah,
Okay.
it's good to have so many
So
questions.
so yeah, I was just wondering from the experimental side.
Yeah.
I mean, we have two photons, right, generated, combined, and then generating one new photon of which has the frequency doubled.
Yeah.
In the actual experiment, do you use like the same photon source, or do you use two similar photon source for this? I mean, for generating this laser, or do you perhaps using one single photon generator and then you split it and then you recombine them, or what, or how?
I don't know about that, but
Mm.
I can answer that.
yeah, maybe Farhan
Ah,
because it's
Yeah.
very much related to this SPDC process, right?
mhm,
Yeah. Usually, if you want to achieve a good second harmonic generation process, I think it would be better to use one laser. So we use one laser and then we use beam splitter to split the beam of light into two
mm,
beams of light, which has the
mm,
same frequency but different
mm,
intensity, and then we
mm,
combine it together using beam
mm.
splitter. Then
Ah,
the combined light goes through like the non-linear material, and then
mm.
voila.
Yeah, that's what I imagine myself as well. I mean, if we were to use two different photon source, it will, yeah, there's a high chance that it won't be coherent
Coherence,
to each
like
other,
yeah,
right? Okay,
correct.
thank you. Mm,
Oh yeah, I don't know if there is some kind of spontaneous second harmonic generation. So in the four-wave mixing case, which is the third order phenomena, there are spontaneous four-wave mixing process. So instead of using two different sources like that, like we split the beam and something like that, we only just shot one beam. We input one beams to the materials, but this four-wave mixing still happens. So we call it the spontaneous four-wave mixing or degenerate spontaneous four-wave mixing. So instead of using two different beams, which initially coming from one beam and then we split it into two and then recombine it again, we just shot one beam to the nonlinear crystal like that. That is the not spontaneous, degenerated forward mixing circuit. But it still happened using only one beams. I don't know about the second harmonic generation. Does it happen to you or not? So, because I rarely play with the second order material. My experience is in the third order materials. Okay, any other question? No? Okay, then I will proceed. Ah, okay. We have talked about the frequency up, frequency increasing phenomenon, which is the sum frequency generation, difference frequency generation, and the second harmonic generation. Now, the second order nonlinear phenomena uh, not only happen one way, like we combine two lights into one light with higher frequencies, but also we can reverse the process. Like we have one beams and then we split it into with lower frequencies. This process is called the down conversion process. And Farhan maybe has very much experience about this down conversion process using the spontaneous parametric down conversion. And in down conversion process, we have the input lights with frequency, what we call the pump frequencies, omega p, and then it will generate two different lights, omega s, which we call the signal photons, and omega 1, which we call the ideal photons. It will generate two lights like this. And these two lights, omega s or omega 1, both of them has a lower frequency compared to the initial photon. So it will lower the energy like that. So the second order not only happen to increase the energy, but also lower the energy. And this down process is especially very, very important process in quantum optics. For example, SPDC, the spontaneous parametric down conversion, can produce the omega S and omega 1 will have some kind of entangled state to each other. So it will be an entangled photon pairs instead of just, yeah, one light and or one photon. It will be one photon pairs. The same thing happens to the four-way mixing process. When we generate light using the four-way mixing process, the generated light will be entangled to each other. They are strongly correlated photon pairs. And this photon pairs may be used as some kind of qubits and some other things in the quantum optics. That's why this down conversion process is very important. Okay. Yeah, this is about the down conversion process. We have to talk about very much process in the second order on. The third order has much more variation of the nonlinear process. But what determines this process and what determines this same nonlinear material to produce like some frequency generation, DFG or second harmonic generation or optical replication or down conversion, what's determine which of this process to happens. As we know, all of them are the nonlinear second order, right? So what's determine this second order nonlinear crystal will produce? We will talk about this is the just surface synthesis degenerate. We will talk about the uh, momentum conservation of the light. So each of this process has a different momentum conservation relation, or we will know is it is much better known as the what we call the phase matching condition. So the phase matching condition determines which of this nonlinear process that happens in set dimension. And the phase matching condition itself is a momentum conservation. So it will so the second order nonlinear phenomena not only relates the frequency of each of the lights that happen when the second order process happens, but also we have to be careful takes the examine the momentum conservation, which is the wave vector of the each of the photons. Yeah, I will explain it about it later. But yeah, this is the oh yeah, this is the degenerate and phase sensitive parametric amplifier. So previously I talked about the parametric amplifier that it can generate what we call it can strengthen one of the beams, be it the signal photons or the idler photons. The parametric amplifier will enhance one of the beams. And there are two types of the parametric amplifier that are being elaborated in the books. Is the degenerate and phase sensitive parametric amplifier. So the degenerate parametric amplifier will produce the signal and idler photon with the same frequencies. So we cannot see the difference between them. And the phase sensitive amplifier means that the amplification process not only depends on the material and the frequency of the photons, but also depends on the phase difference between each of these photons. So this amplification can happen if the phase difference between the pump photons and the signal photon or the idler photon in the degenerate case is equal to zero. So it will produce such a some kind of a constructive interference if the phase difference is zero. But the amplification process happens when the phase difference between the pump photon and the signal photon is equal to 90 degrees or pi over 2. So it will produce what we call the destructive interference. The photon will disappear. So we can do a variation of the phase of the photons, the input photons, the pump photons, to manipulate the amplification process like that. We can amplify or de-amplify the generated photon, which is the signal, or in the degenerate case, also the idler photons. Okay, is there any question so far about this down conversion process and yeah, phase sensitive amplifier?
I don't have any questions.
Okay, Handoko?
Yep, you can continue.
Okay. Yeah, this is what I mentioned before to Farhan first question. Maybe when we see the equation number 15 here, the equation 15, we can we can see it more clearly that the second order process is not only happen to the E square, but instead it is a tensorial summation of the electric field and also the second order, the second order susceptibility tensor. And as I mentioned before, the higher the nonlinear order process, the order of the susceptibility tensor will also increase. For example, in this case of the second order nonlinear susceptibility tensor, we have the second order nonlinear susceptibility tensor have some kind of ij and k index. And this ij and k index usually denotes what we call the Cartesian coordinates. So we have some kind of I2 xxx, I2 xxy, I2 xyz, and like that. So the tensor itself will depends based on the Cartesian coordinates. Like it depends on the alignment of the crystal. And also this second order tensor chi2 can be expressed in the D tensor of this. And what we call this D tensor is the nonlinear optical coefficient tensor. So it's just some kind of another way to express this chi2 tensor using this second order, second nonlinear optical coefficient tensor. But to be perfectly honest, I have no experience in using this notation in equation 16, so I cannot explain it any further. But what I can explain is that symmetries play an important role to the second order nonlinear process. So it will determine what kind of the components that we have in the optical coefficient tensor. Some value might have a zero value due to the symmetry, and some value may also have the same value. Some let's say that D11 may have the same value as D36, and then the rest of the tensor are zero. It will it will be much more useful because it will make the tensor itself become much more simpler. So is a great simplification using the symmetries of the crystal structure. Okay. Okay, so yeah, this is what I mentioned before about the phase matching. The phase matching itself, what determines which one of the nonlinear interaction that happen inside the same nonlinear second order material. Not only second order, but the phase matching also happens in the third order material. So the phase matching itself basically the momentum conservation relation of the photons, which can produce when the photon interact with each other, it will produce what we call the constructive interference when they have the same phase matching. For example, in the equation 17 here is the phase matching condition for the sum frequency generation. So the sum frequency generation, we want to generate the new photon with frequency omega 3. And this photon of omega 3 frequency has the wave vector of k here. And k1 is the wave vector of the first fundamental photons, and the k2 is the wave vector of the second fundamental photons. When the sum frequency generation happen, we not only see the frequency summation, but also we have to take carefully that the wave vector must obey this relation also. And another example for the case of the second harmonic generation, the K1 and K2 will be the same, right? So the the phase matching condition will satisfy this equation again. So K parenthesis omega 2 is the wave vector of the generated photon, the second order, the generated photon from this second harmonic generation with the frequency of omega 2. And K omega here is the wave vector of the initial input photon with the frequency of omega. So the wave vector of the generated photon will have twice as much as the value of the wave vector of the initial photon in the case of phase matching in the second harmonic generation. Okay. However, there are some other factors that we have to carefully take because the perfect phase matching is usually rarely happen in the material due to what we call the effect of dispersion. When the dispersion happens inside the material, the wave vector itself will be shifted, right? Because the material refractive index may change depending on the frequencies. So there will be some kind of phase mismatch between them. The phase mismatch itself is caused by the effect of dispersion. So, for example, the second harmonic generation, the wave vector of the omega 2 must be equal to twice as much as omega 1, right? Like this. But in practical use, the wave vector of the omega 2 may be slightly larger than twice as omega 2, like omega 2 times the wave vector of omega plus some kind of value, some kind of constant, or maybe slightly lower than twice of the initial wave vector of omega. So 2k plus minus some kind of value. And that kind of plus and minus happens due to the dispersion of the material. And for the second harmonic generation process to happen perfectly, we have to make that kind of plus and minus of the k as small as possible. And we can do that in the second order material using the birefringence effect of the medium. Before I explain about the birefringence, is there any question after this?
No question.
No question. Okay. What about Handoko?
So basically this plus and minus factor that you mentioned depends pretty much on the quality of the material, right?
Yeah. Yeah.
Yeah, so the better the quality of the material is, the more it will satisfy the equation mentioned here.
Yeah.
Yeah.
yeah, roughly say roughly like that.
Mm.
I say it roughly like that because not only as
Mm.
what how can I say? In my experience, it's not only depend on
Mm.
the how good materials that we have, because material may have some kind of defects, right? In
Mm.
their kind of crystal structure or something.
Mm.
But also when we have these materials and then we kind of create a waveguide using it, it also depends on the geometry of the materials of the waveguide that we have using the materials. So there are so many factors that can affect this phase matching condition. Yes, what you mentioned is right. So the material quality, the defects between in them, it's pretty much affect the phase matching condition. But also there are another effect. Dispersion is one of them, and dispersion not only caused by the material types, but also the geometry of the waveguides, and also maybe some kind of coupling to the another phenomenon.
Mm.
So it is possible that one second order of nonlinear phenomena is interacting with another second order nonlinear phenomena. So we have second harmonic generation light, and then we have what we call the sum frequency generation light. And these two new generated light may as well some kind of interacting with each other. And it will cause another problem, but it is very complex problem.
So yeah, I can imagine that it will, yeah, this will be hard to be, done on experiment, as it really depends on the quality of the material itself.
Yeah,
I mean, even the same material that looks like the same, but if one of them is more dispersive of another, let's say, yeah, it will kind of greatly affect this. So
yes,
yeah.
of course.
Mm.
And even one material with the same quality, with the same waveguide, may also
Mm.
produce different nonlinear interaction. As for example,
Mm.
in my case, doing the four wave mixing, I use the silicon nitride. And the silicon nitride may has a different quality of nonlinear interaction depending on how we fabricate the silicon nitride. Let's say we fabricate it using the low pressure chemical vapor deposition, LPCVD. And the
Mm.
another way is using the plasma enhanced chemical vapor deposition, PECVD. Both of them
Mm.
has a different quality of the nonlinear interaction. So it has the same material. I made the same wavelet using the same geometry and something.
Mm.
But due to the difference of the fabrication process, it still show some kind of difference in the nonlinear process that in the experimental point of view. So yeah, there are so many factors in this phase mixing condition.
Yeah, I guess there have to be some factors that, affect the, I don't know, the parameters of the material when it is grown by using two different techniques. And even those, from what I imagine, even those grown with the same fabrication technique itself would need further investigation, right? Like the ideal parameter that is, optimal for the fabrication of the material itself, and etc. So
Yeah,
yeah, okay.
yeah,
Yeah,
it's
okay.
very right. But
Mm.
unfortunately, I have no experience in the fabrication because we don't have that
Oh.
setup in Indonesia. Yeah,
Mm.
too
Okay, I
bad.
think that's all. Thank you.
Okay. Any other question? No? Okay, then I will continue. Okay, so this is the phase matching in the dispersive media, which I mentioned before. So when the dispersion event occurs, the light with different frequencies will travel at the different speed with the different velocity or speed inside the material. And this different speed or velocity will cause the change in wave vector because wave vector is related to the momentum of light. So it will be related to the speed or velocity of the light inside this materials. And one of the cause of the dispersion is the refractive index dependency on the frequency. So the refractive index may as well changes due to the changes on the frequency. Now, and this dispersion effect will cause the mismatch between the combination of the waves, the generated wave from the nonlinear process, and the fundamental waves that are interacting inside this material to generate the new ones. Such as this is for the example of the phase mismatch in the second harmonic generation. I took this from the RP Photonics website because it has some of basic information of the photonics domain. So instead of K1 and K2 combine and then produce K1 and K1 combine exactly to have the same value as of twice as the with the K2 generated with the twice as much as K1 twice as K1, we have some kind of difference here, delta K. So this delta K is what I mentioned before to be the phase mismatch, the plus and minus from the dispersion effect. And when this delta K happen, we can calculate the phase mismatch is by taking a difference between the generated light wave vector with the initial light, which is the K1 and K1. Yeah, so K1 minus twice K1 in the equation 20. And one of the ways to cancel the phase mismatch is using the birefringence of the material. So birefringence is that the refractive index of the material not only depends on the material, but also from what direction we input lights. So it's the refractive index dependence on the optical axis. So the axis of the or direction of where we input lights, like that. That's what we call the birefringence. And by using the birefringence, we can achieve two kinds of phase matching condition. The first one is the type 1 phase matching. This phase matching condition occurs when we have two fundamental beams with the same polarization. And these fundamental beams has the perpendicular polarization to the generated beams. So let's say that the fundamental like K1 and another K1 has the polarization to the y-axis like this. And then when it enter the birefringence crystal, it will generate the K2, the generate like with the polarization of the x-axis like this. So it has the perpendicular direction. So usually in terms of the birefringence, we have what we call the ordinary axis and the extraordinary axis. Just basically just a difference between the polarization. Ordinary axis means that one light directed to one axis, and extraordinary axis means the light which will be polarized to the other axis. And usually they have some kind of perpendicular direction to each other. So in type 1 phase matching, both of the light either will be ordinary or extraordinary and extraordinary polarization. And the second phase matching in the birefringence crystal is the type 2 phase matching. And this phase matching can occur when the fundamental beams K1 and another K1 has the different polarization. So let's say that we have K1 in the ordinary axis and the second one is the extraordinary axis, and then it propagates to the material, to the birefringent crystal, and then it will generate the K2. The K2 will be in between the ordinary and extraordinary axis, like that. So for example, here in the second harmonic generation, when we have the negative uniaxial nonlinear crystal, the negative uniaxial means that the refractive index in the extraordinary axis is slightly lower than the ordinary axis. We have that the refractive index of the generated light, which is different from the refractive index from the initial frequencies due to the effect of dispersion, is slightly larger than the refractive index of the initial photons. And this we can achieve type 1 phase matching in this negative uniaxial nonlinear crystal by using by setting that one fundamental beams as ordinary rays and the generated beams as the extraordinary rays. So that if the fundamental beam is the ordinary rays, which means that and the generated beam as the extraordinaries, we can reduce this value of refractive index of in the generated beams to slightly lower, so that it can has the same value to the refractive index of the fundamental beams, so that it will be equal. So it will satisfy the equation 19, which is basically the perfect phase matching condition, like that. This is one of the example. And this equation is what relates when we have the optic axis, the ordinary axis or extraordinary axis, not directly related to one of the Cartesian coordinate, but some kind it has an angle of deviation theta. Yeah. Then we can what we can vary or play with the angle of deviation to achieve this extraordinary or ordinary phase matching condition using equation 21. The equation 21 is the equation for the type 1 phase matching for the second harmonic jet. In this kind of birefringent crystal with the optic axis that has some kind of angle of deviation. Like that. Okay. Is there any questions so far? No?
No, no.
Handoko?
Yeah, I'm still thinking what to ask, so you can continue.
Okay, that's all. If there are no further questions, that this is the end of this our section today. So we finished the nonlinear optics. Basically, the Markov books only talk about the second order nonlinear, but hopefully later we will also introduce or play deeply with the another third order or higher order phenomenon. Okay, that's all from me. Thank you very much.